Welcome to our tutorial about point groups. The goal of this tutorial is to get you familiar with the symmetry of molecules and how it relates to their chemical and physical properties. The mathematical toolbox which we need to characterize molecules with respect to their symmetry is called group theory. We don't need to understand all the math behind this theory in order to solve problems with it. In very simple words, a group is an algebraic structure which allows us to do multiplication of the elements within the group. Let's call our group G. And let's say that the elements A, B, and C are all elements within that group. And later on we will see that the elements A, B, and C are actually our symmetry operations. There's also an operation defined between A and B, and the result of this operation is also element of our group. We actually will only deal with multiplication operations in here, meaning that what we are writing down here as A dot B is actually the product of A and B. In addition, there's the associative law valid, meaning that A times, in brackets, B times C is equal to A times B, in brackets, times C. Every group has an identity element, which we write down as E, or sometimes in literature you will also see a 1. This identity element you can imagine like a multiplier, which is 1, and if you multiply something by 1, you just end up with the same number. And every element has an inverse element. Usually we write down the inverse element of A as A to the minus 1. And what this means is that if you multiply A with its inverse element, you end up with the identity. Now let's look at some examples here. Let's say we have a square. And let's see what our elements, the elements of our group, can actually do with this square. Now I already indicated to you that these elements are actually symmetry operations. Now let's think about which symmetry operations can we perform here with the square, so that after performing the symmetry operation we get the same square, meaning without deforming the square or without rotating it in a weird angle, we just find the same figure after doing the symmetry operation. Now, just in order to make things a little easier for you to see, let's give these corners numbers 1, 2, 3, and 4. And let's say we do rotation. Let's start with a rotation around an angle of 90 degrees. The result here is not too difficult to guess, so you end up with a square which looks like the square which went into this experiment here. 1, 2, 3, 4, just the numbers changed. Whereas if we do a rotation around 45 degrees, it will look slightly different. It will look somewhat like that. 1, 2, 3, 4. And if you superimpose the first square and this square, you will see that the corners don't really overlap, meaning that 45° is not an operation which will transform this square into itself so that these two squares, the initial one and the final one, are actually superimposing. Now let's take a look at another example, but let's just stay with our square. And now let's make it a little bit more complicated by doing a combination of two symmetry operations. Let's first introduce our elements. Let's say that A is a rotation around 90°. And let's say that element B is a reflection. And in the first step, we will see what happens if we apply A times B to our square. Well, let's do the experiment. Say we have again our square here. 1, 2, 3, 4. And what this means here is that first we have to apply B and then we apply A, meaning first we reflect, and now we need to first find one of our reflection planes. Let's use this one as our reflection plane. And do a reflection with it, meaning apply symmetry operation B. And the result is that after doing this reflection, 2 becomes 3 and 3 becomes 2, meaning this is 3, this is 2, and 4 becomes 1 and 1 becomes 4. Here we have 4 and here we have 1. And the second step is now to do a rotation. Rotation by 90°, which is symmetry operation A. Now let's look at our square. What happened to it? This one becomes 1, this one is 4, this one is 3, and this one is 2. So this is the result of A times B. Just out of curiosity, let's apply B times A and see if we get exactly the same result. Now you can guess what will actually happen here. So let's apply this to our square. So we start out with exactly the same square. 1, 2, 3, 4. Step number 1. Now we have to apply A first, which is a rotation. Now what's the result? It is actually a square which has these corners 1, 2, 3, and 4. And then we apply symmetry operation B and end up with a square after reflection, and just mark the reflection plane here again. It's again here. So if we do the reflection, 1 becomes 2, 2 becomes 1, 4 becomes 3, 3 becomes 4. Now let's compare this square and this square. Now, if you look at the corners, those don't look equivalent. 4 overlaps with 2, 3 with 1, 1 with 3, and 2 with 4. That's the result of B times A applied to our square, meaning that A times B and B times A gives us a different result. Now, there's absolutely nothing wrong with it, but we need to remember that the group which we are using is not commutative. Let's just write it down. Group is not commutative. We say also our group is not abelian, meaning that it really matters whether you apply a certain symmetry operation first or second.